Hi everyone, this is Chandrakant Mishra. Today we are going to discuss the network theorems. Network theorems is an important part of the network theory, and without the knowledge of network theorems, your network theory course is incomplete. Also, network theorems will help you solving the gate question with edge. Learning all the network theorems and its application will greatly reduce the efforts needed to solve the gate questions or any engineering competitive exam questions. Also, you will be applying the network theorems in analog electronics and in the analog electronics of the circuits like which involves the MOSFETs, BJT. Also digital electronics, especially the logic gates parts. So let us discuss the network theorems one by one. First thing you should remember that in this analysis we'll assume that all the networks are linear. What do you mean by the linear networks? Where the voltage and current have relation of straight line. That is, V is directly proportional to I, not V proportional to I square or root over I. Remember that all these not included in the linear network. So we are going to discuss all the theorems, keeping in mind that we are dealing with linear network. Broadly, we can define linear circuit as a circuit composed of entirely of independent sources, linear dependent sources, and linear elements. Linear dependent source I have already discussed in the network basics. First, we are going to superposition principle or superposition theorem. Whatever the definitions I have written, you can go through, but it is simply in any linear network consisting of two or more sources, maybe voltage source, current source. You can consider the network with a given source and all other source reduced to 0, then algebraically adding their responses. But one thing you should keep in mind, replacing the independent source only. Linear dependent source are active in every experiment. So whenever you have a dependent source, you cannot reduce it to 0. Only independent source you have to reduce to 0 while considering given source. Independent voltage source replaced by short circuit. The voltage source, independent ideal voltage source, should be replaced by short circuit because its internal impedance is 0. Similarly, independent current source ideal is replaced by open circuit. So we'll clarify more into this network theorem with example. We'll deal with a very simple example. Find the current through 6 ohm resistor in circuit shown below. There are many ways to solve this question, but we are mainly intended to solve through superposition theorem. According to the superposition theorem, what we will do? First we will consider 6 volt source. So I have to reduce 2 ampere current source to 0 because it is a independent source. So considering 6 volt source, so I keep only 6 volt source and reduce 2 ampere current source to 0. So what will be its internal impedance? Infinity, because it's a ideal independent current source. So the circuit will be opened here at this terminal let's say it is AB, so AB is open. Now you can find out the current. I due to the voltage source alone is the 6 upon, so it is a simple circuit, 6 upon 3 plus 6, which is 2 by 3 ampere. Next, we'll reduce 6 volt voltage source to the 0 and consider only 2 ampere current source. So next circuit is like this. So it is a current division. So current due to current source only, current division rule. So IIS is the 3 upon 3 plus 6 into 2, that is 2 by 3 ampere. So I have calculated current due to the current source and current due to the voltage source. So last step is to add individual responses algebraically. So both I have to add to get the complete response, which is 4 by 3 ampere. Quite easily done. Consider this. Here intentionally I have given 3 sources, 2 milliampere sources, 12 volt sources and 6 volt sources. Find I0. I0 is the current through 2 kilo ohm resistors as marked in the circuit. So with only 2 milliampere source active, so I have to reduce the 6 volt source to 0, so it will be a short, So you can see it is the branch, it is shorted here and it is also shorted here. You can see that these 2 kilo are in parallel, and this 2 kilo here and this 2 kilo here. I have redrawn the circuit. So I0 will be the, simply you see the current same, it is the same, a single node, the common node of 2 kilo ohm resistors here. So current will be divided equally. So 2 milliampere upon 2, which is 1 milliampere. This is the current I0 due to the 2 milliampere current source. Now with 12 volt source alone, here is the 12 volt source. So 12 volt source alone, so this will be, this 6 volt source will be short circuited and 2 milliampere current source will be open circuited. So you can see easily that this is the same node in a simple single node. This side is open, so no current flows in these two resistors. So I0 will be the 12 upon 2 plus 2 kilo, that is 4 kilo. So 12 upon 4 kilo, you get the 3 milliampere. This is the current due to the 12 volt voltage source. Now last one is the due to 6 volt voltage source. So this is open here, this is short, and this is the 6 volt voltage source. Now just look at here, this 6 volt voltage source, this is one branch connected across the 6 volt voltage source and another branch, and this is the terminal positive, this is negative. So this I0 will be the, because current will be flow this direction and this directions, but the I0 has been marked in the opposite direction, that's why negative sign. And this current will be flow this way, this sense. So 6 upon 2 plus 2, 4, that is the minus 1.5 milliampere. Now when all the sources are acting together, the current I0 will be the algebraic addition of all three I0s, that is all three currents. So we'll do another example with a dependent source. The current I as shown in the figure. Find the current I. That is, we have a 12 volt independent voltage source, 7 ampere independent current source, and you can easily see here 3I volt voltage source, where I is the current through the 3 ohm resistor. So we'll apply the superposition theorem. As I have told you already, only independent sources can be reduced to 0 and dependent source will be acting as it is. So first we'll consider the 24 volt independent voltage source. So this is the current I designate as the current due to the 24 volt voltage source alone, that is IVS. So obviously this dependent source variable has to be modified, because whatever the current flows through the 3 ohm resistors, that current is multiplied by 3 to have a dependent voltage source. Now apply simple KVL here. 3 IVS, 3 plus 2 5 IVS and equal to 24. So IVS, that is the current due to the voltage source or 24 volt voltage source, is the 24 upon 8 3 ampere. One part over. Second, when the current source acts alone, that is voltage source short, current source alone, so I designate it as the current due to the current source IIS. So this will be the 3IS, the value of this dependent voltage source. So 7 ampere is coming upward. So at this node they are together. So this will be the IIS plus 7. So apply KVL in the outer loop. So 3IS plus 2 into IIS plus 7 plus 3 IIS equal to 0. So 8 IIS is equal to minus 14. So IIS will be the minus 14 by 8. You will get minus 7 by 4. So now when both independent sources are active, the total current will be the algebraic addition of the individual responses, that is 3, and this is the minus 7 by 4, that is 5 upon 4, and you get the 1.25 ampere. So you can see that in this question superposition theorem helps us greatly in analysis of linear circuit. I hope this theorem is clear with 3 examples. Let us move to the source transformation. Source transformation is a simple process. When you have voltage source, you can transform into the current source. How it is done? You transform a voltage source to the current source by dividing the series resistors. So Vs upon Rs, this will be the current source Is, and connect the series resistor with in parallel with the transformed current source. Simple. Equivalently, if you have current source and parallel impedance or resistance, so it can be converted and transformed into the voltage source. The voltage source value will be the Is multiplied by Rp, and series resistor will be the Rp. Remember the orientation. This plus minus, the orientation of current is this. This is the flow of current. So orientation of the voltage. So let us try with an example. Always remember, when there is a dependent source, if dependent current value is here, so if you transform this to a current source, then dependent source will give error, because now this resistor has been transformed, so it will not give the correct result. So this is only one point. Whenever a dependent source is there, so be careful, don't transform into the source transformation for that voltage source. For example, I'll highlight here, that is, suppose you have been given like this. Let's say 5 ohm, 4 volt, 3 ohm, and this is the dependent source of 2I. What is the I? I is the flowing through this. And they ask you to find the value of current I. See, you can transform, but end result will be wrong because the current is flowing through the 5 ohm resistors. If you transform into the current source, this branch is lost. Find the current through 10 kilo resistor as shown. This is the 10 volt, this is the 5 kilo, this is the 1 milliampere, and this is 10 kilo. So you can easily make source transformations. 10 upon 5, that is 20 milliampere. 5 kilo, 10 kilo, and 2 milliampere. So 5 kilo, 2 milliampere, 1 milliampere, both in the same directions, and they are in the parallel. So from the basic you can add this. Now 5 kilo and 10 kilo. So now current division. So current division tells that current through this 10 kilo is the 5 upon 5 plus 10 into 3. So 1 milliampere. So while solving the questions in the competitive exam, keep your mind open so that you can apply appropriate theorem quickly. Now we'll move to the Thevenin's theorem. This is the most used and most prevalent theorem and most important as far as GATE exam is concerned. Every year of GATE paper, directly or indirectly, you will find the question based on the Thevenin theorem. Another one is the Norton's theorem, that is the dual of the Thevenin theorem. Knowing the Thevenin theorem, you can easily find the Norton's theorem also. A linear two-terminal circuit can be replaced by an equivalent circuit consisting of a voltage source VTH and series impedance ZTH. But how you find the VTH? How you find the ZTH? Where VTH is the open circuit voltage at the terminals and the ZTH is the impedance of the networks looked back from the terminal with all independent energy source replaced by their internal impedances and dependent source are operating. Graphically, I want to explain this. This is the linear network. First of all, understand network should be a linear. This part is immaterial whether linear non-linear, but where you are applying the Thevenin, that must be linear. So now you measure this voltage, make the circuit open and measure the voltage. That is your Thevenin voltage. Then reduce all the independent sources to 0 and replace their internal impedances and consider all dependent source operating. Then measure the impedance at the terminal AB looking back into the network. That is your ZTH, Thevenin impedance. Now equivalent circuit at the terminal will be this VTH and ZTH. A voltage source in series with an impedance ZTH. And this is your load as it is. So now you can connect and find the response. We'll go to the example to clarify more about this theorem. Find the Thevenin's equivalent circuit at AB. This is the A and this is the B. And find the current through 2 ohm resistors. So as per the Thevenin theorem, your VTH is the open circuit voltage at the terminal AB. That means here I have opened, so you have to open physically at the terminal A and B, then find the open circuit voltage. Once you open, you see So no current flows through the 4 ohm resistors. So voltage across the terminal AB, that is open circuit voltage across the terminal AB, is the simply voltage drop across 20 ohm resistors. So VTH is the 20 upon 5 plus 20 into 50, that is 40 volt. ZTH, according to the Thevenin theorem, reduce this voltage source to 0. This is the ideal voltage source, so it will be short. You can see that 5 ohm and 20 ohm resistor are in parallel, and these together are in the series. So 5 parallel 20 plus 4, you get 4 plus 4, 80 ohm. Now replace the circuit AB with Thevenin voltage and Thevenin impedance. Thevenin voltage we have found 40 volt and Thevenin resistance 8 ohm. Now connect the load resistors of 2 ohm. Now current will be the 40 upon 8 plus 2, 10, that is 4 ampere. So quite simple. Those example was also very simple. Thevenin resistance can also be defined as ZTH is equal to open circuit voltage. Like this is your network. Let's say I want to find the Thevenin resistance across AB. So find open circuit voltage. Now find the short circuit current. So you can divide. So VOC is the open circuit voltage across the terminal AB. ISC short circuit current at the terminal AB, as I have demonstrated here. We'll discuss another example. Find the Thevenin's equivalent circuit with respect to terminal A and B for circuit shown below. This terminal is open, so find the Thevenin voltage at the terminal A and B. So the circuit though looks complicated, but you have to apply the KCL here. So KCL at the node A, this current and this current. So this current, first this current 30 minus V2 upon 40 plus 1.5, and outgoing current, that is V2 upon 60 plus 20, that is 80. So you got the V2. This is your V2 with respect to ground. This is not your VOC. VOC is this voltage across the 60 ohm resistors. That means a potential division of the V2. So VOC is the 60 upon 60 plus 20 into 60 volt, because V2 is the 60 volt. That gives you 45 volt. So therefore VTH is equal to 45 volt. Now come to the Thevenin resistance. As I have told you, so better is to find the short circuit current here. So make a short circuit here between A and B. Once I made a short circuit, this current is 0. So again KCL at node A, this current and this current. So 30 minus V2 upon 40 plus 1.5 and V2 upon 20. From here I got the V2 equal to 30 volt. So now ISC will be this is your V2. So this current, no current flows here. So V2 upon 20, that is 1.5 ampere. So RTH will be the VOC, that is open circuit voltage across the terminal, upon short circuit current through the terminal. So 45 upon 1.5, that is 30 ohm. Now this is your answer. Only practice makes man or woman, perfect. Okay, now suppose you have dependent sources, what you will do? You can use this way. Also I will discuss the another way. If a network has linear dependent source, RTH can be found as previously discussed this way. That is, RTH is equal to open circuit voltage upon short circuit current. Or network with you reduce all the independent source to 0, replacing their internal impedance, drive the terminal with the voltage source and measure the current going to the network. So RTH will be V2 upon I2. Or you can connect a current source, measure the voltage across this current source. To make calculation simplified, most often we use I2 equal to 1 ampere. So V2 upon 1 ampere, that is V2, is numerically equal to RTH or ZTH. So let us start with an example. Find the Thevenin equivalents for the circuit shown below at terminal A and B. Thevenin voltage you can easily find out. No current flows, that is voltage across this terminal. Use a KVL, that is 6I minus 2I plus 6I equal to 20, that is I equal to 2 ampere. So VTH is equal to, that is 12 volt. Now we calculate the Thevenin impedance or Thevenin resistance. Connect a 1 ampere current source, then analyze the circuit and find the V2 using KVL in the loop 1. Now you see 1 ampere is coming here, so here I ampere is going, so resulting current will be the 1 minus I. So now apply the KVL around this. So 6I minus 2I minus 6 into 1 minus I equal to 0. From here you got I equal to 0.6. So therefore V2 will be the 6I plus 10, that is 13.6. So your Thevenin resistance is the numerically equal to V2, that is 13.6 ohm. So your Thevenin voltage was the 12 volt and the Thevenin resistance is the 13.6 volt. Hope you understand this example. See you in the next class. Thanks for watching.